Oh, hey folks, welcome to lesson 7.3. This is about the shell method, one of maybe my favorite in AP calculus applications, the shell method. Now, if you can see really close here, it's kind of hard for me to get that up there, but this is it's a bushing, okay? That's could be part of could be an axle going through there, could be a shaft going through there, and it could be housed inside an engine. I actually used this, I ordered this and used this for my weed eater to keep myself from having to buy a new weed eater. Little shaft at the bottom going around to cut, and it's pretty cool. But you see the idea of a shell. Now let's talk about the basic idea of a shell. So, well, before I do this illustration, let's just do this illustration now. So here we go. I have like a little rectangle, okay? And I'm going to spin it, spin it, spin it, okay? See if I go this way. I don't know how that comes across, but if I kept on spinning it, you would see that it would make a shell, okay? Let's try to do that. Yeah, that's not bad, okay? It would make a shell of a certain width, and that width would be what? It would be that angle, that rectangle right here, okay? All right, very good. Okay, so this is part of your book. You want to find the volume of a solid of revolution, and we want to compare the disk and the shell method. All right, so here's a picture, okay? Here's a picture, looks like a bushing like I just showed you, but it's a shell. And look at this little rectangle up here at the top, okay? So this is the idea, and there's certain measurements. See, there's this inside radius, and there's this outside radius. There's W, which is the width of the rectangle, okay? Now, if you look carefully, in the text, this is explained pretty carefully, and we've got this detail of the inner and the outer width, and what they're doing is they're using that to derive this little formula, okay? And this formula can be seen in the lower right-hand side. So again, they're taking a rectangle, they're revolving it around an axis, and they're trying to develop this formula. Let me try to explain that. I'm going to try to do my best. Here's my version of the little shell. Now remember, we got the outside radius and the inside radius. I'm going to call the inside radius a little r, big R, and then W is the width, okay? Now remember, if W is the whole width, W over 2 would be half the width. So if you look over here at this part, okay, notice we have P, which is going to represent the average radius. So the inside radius is P minus W over 2, and the outside radius is P plus W over 2. So outside radius, inside radius. And now what we're going to do, we're going to use these to develop the idea of the formula. Remember, the volume of a cylinder is equal to pi r squared h. That was it's probably inside the front of your book. But anyway, so the volume of the shell would be the outer cylinder minus the inner cylinder. So if you look at this illustration, I could factor out the pi and the h, right? The pi and the h, and I'd get r squared minus little r squared. Now what I did is I played with this, and I actually multiplied out the big R squared, and I got this, the little r squared, and I got this. Please pause it to make sure you understand how I multiplied those two binomials out. So big R squared minus little r squared is blah, okay? And then what I could do is I could simplify that. Let's see if I can move this up a little bit. So everything else goes away except the PW and the minus negative PW, and that would be 2PW. So in essence, the volume of that little shell, which I'm right here, okay, is equal to 2 pi, the radius times the height times a little width. So in this particular example, delta V is equal to 2 pi. It's the x, all right, the x value or the radius times the height, which would be the y value, and times the width, which is delta x. So hopefully that helps you understand where we got the little formula down here for a rectangle that's revolved not around the x-axis, but around the y-axis. Let's see if that works. So what exactly happened at the end of that last segment here. But anyway, I'm back here with you, and we're trying to illustrate the idea of the shell method. And so you could see I've got it set up. And here's this little illustration of a rectangle being revolved around a certain axis. Let's see if I can get that to work out for you. So we got the blue guy. Remember, that was the disk guy. And I got this, looks orange, but really it's red. So I'm revolving that around. I'm probably talking at the same time, so. Looks like a little washing machine basket. So anyway, I could do that, and we could show the locus or the set of rectangles inside there, and hopefully that little illustration helps you understand how we could find the volume of a shell, okay, using that rectangle and revolving it around. And then what we do is just put these shells inside of each other. I'll show you what I'm talking about. Probably be easier to show this on the little document camera, but several years ago I obtained this set of illustrations. Anyway, what it is, it's several shells together. A little hard for me to get you to see all of that. So I got a shell there, then I got another shell here, and I got another shell here, and they all go together and form a solid. Okay, that makes sense. So anyway, they're right all in here together. Okay, all right. Another way to look at it is if I took a piece of paper and I wound it up, okay, and they're like separate shells. I could find the volume if I added all the separate shells together, and I had the shells to be really thin. So hopefully that makes sense. I have to tell you, I was going to do this from scratch, but I ran out of time, and plus my wife wants me to go to the grocery store. So anyway, we're going to look at example 1 in the textbook. So example 1, I have this function right here, and they want you to revolve the region bounded by the x-axis, or revolve it around the y-axis. So if I say this once, I say this a million times. The way to be successful at these problems is to take it step by step. You're not going to want to, okay, but it's worth it. So the first thing I do is I put a graph here, and I graph my function. Now I know what I'm looking at. It's this region right here, okay? So I put a little rectangle in there, and I'm revolving it around the y-axis. So I'm going to get something that looks like this. Now you may remember I told you before, have a little element that you can work on to be able to develop a basic piece. And that way you could accumulate all of them to do your real actual volume. So here's my little piece, delta x, that tells you we're going to have things in terms of x. So it's the radius, which is x, times the height, which is the value of the function. And I'm just going to leave the 2 pi out there in the front. Okay, so there's my x, there's my y. I sort of cheated, I just multiplied that out. I did the antiderivative, remember going from 0 to 1. And remember it's blah minus blah, but the second blah is going to be 0. So 2 pi, and I got 1/3 minus 1/5, right? I'm plugging in 1. Now we know from fractions that's 5 minus 3, or do it on your calculator, whatever. And I get 4/5 pi u cubed. You can almost see that at the bottom, okay, and that's correct. So that's that example 1. Example 2 in your book is really interesting. So here's this function, and you got to revolve the area bounded by the y-axis and y equals 1, that should be y equals 1, around the x-axis. So you may wonder how I got this graph right here. What I did is I solved the function for y, and it was y is equal to like radical negative ln of x. It's just crazy. But anyway, I graphed it, and it did look like that, which is really strange. But so here's my rectangle. Notice I have delta y, so we're going to have to use y. I've got the radius, which is y, and I've got the height, which is the x. So notice I'm going to write my formula, or I'm going to put it in the formula. So I got my 2 pi, got my 0 to 1, because I'm going from 0 to 1. There's my x, there's my y, there's my dy. Now, we're going to have to recognize this as a u du. So u is negative y squared, so du would be negative 2y. I worked my magic on this integral right here. Remember, the antiderivative of e to the u is just e to the u. And so then I wrote e to the u. I put my values in there. Well, what happened over here? Well, those 2's divide out, so just negative pi. I evaluated, and I did a little manipulation here. You can call that algebra if you want to. And I got 1.985 or 1.986 according to the people from the AP. All right, now there's a lot going on there. So let's get back to the lesson. I developed the formula. Okay, hopefully that made sense. Notice how this bushing is formed if I revolve it around the x-axis. There's a little Riemann sum right there. Now, the formulas are important. So here they are together. dy dx. This makes sense. It's just the little width of the circumference of a circle times the height. That really actually does make sense. Here's that example 1 problem, which I did from scratch. I wanted to do live, but we just ran out of time. 4 pi over 15 was a correct answer. Let's look at the second example. So here's the example they gave you, and they did it very similar to the way I did it. Okay. I really like the little exploration there. I'm telling you, you guys have a great book. Okay. It is a little heavy. Okay. You should get PE credit for hanging that around there, but keep that in mind. And then sort of at the end here, we're comparing the difference in the disk and the shell method. So hopefully that helps you take a good solid look at this part of your text, and it'll explain it to you in a way that hopefully makes sense. Now, the last thing I want to do is just take a minute and talk about how the shell method sometimes is preferable. This is why we're going through all the pain here in this effort here. So here's a function, and we're using the shell method. Notice we're splitting it up into 2 different parts. Okay, that makes sense. Now, here's a problem with a pontoon, and here's a problem that illustrates why you actually have to use the shell method here. Because if I had some function y equals blah, and I wanted to use the disk method, I'd have to solve that for x, and that would be basically impossible. But see how easy this integral was once you got it set up? All right, let's pause. Okay, so this lesson is good for folks who you're using the textbook and you have all the resources and you're working the problem and you want some more understanding. I'm going to make this lesson optional, but it's a great lesson for you to enjoy going further and solving some really sophisticated things. I hope you enjoy it. Thank you.